All right, let's do the radical functions and radical worksheet. All right, as I tried to explain in class, the 1/2 power, if you had x squared equals 9 and you wanted to get rid of the square, you would take the square root and you'd get x equals, and of course, plus or minus 3. But if you had x squared equals 9 and you decided to take it to the 1/2 power, and when you've got a base to a power, you multiply the powers. 2 times a half is 1, or half of 2 is 1. You get x equals 9 to the 1/2, which is plus or minus 3. So 9 to the half is the same as the square root. So this is saying a function that's the same as the square root of x. And so the domain, what kind of numbers can you take the square root of? Well, you can take the square root of 0 and anything positive, but not negatives. This means the cube root. Now, the 2 cubed is 8, so the cube root of 8 is 2. Negative 2 cubed is negative 8, so the cube root of negative 8 is negative 2. So you can take the cubes of negatives. Now, there's nothing squared that will make a negative 9 that's real. You have to go to imaginaries. But you can get negatives by cubing, and so you can take the cube root of positives, negatives, or 0. So this is anything from negative infinity to infinity can be used. Now you can type x to the 1/2 power in your calculator. It will look like what we've talked about, half of a parabola this way, and you can only use 0 or greater. If you type in x to the 1/3 power, it's going to look like the cube root, which is the cubic function on its side, and it exists for all positive x's, negative x's, and 0, for all real numbers. So this or this. The 1/4, the graph of that's the 4th root, and there's a button for doing that in your calculator. But the 4th root, well, the x to the 4th sideways would look something like this, and so the 4th root is simply this, or the domain would be 0 to infinity. You can't take the 4th root of something negative. There's nothing you can take to the 4th and come up with a negative answer. Now 2 to the 4th is positive 16. Negative 2 to the 4th, if you put parentheses, is positive 16. There's no way to take something to the 4th power, an even power, and get negative numbers. So you can't do 4th roots of negatives, only the positives, or 0. Now 5th root, you can take negative 2 to the 5th, and you'll get negative 32. So you can take the 5th root of negative 32, which is 2. You can do these for all real numbers, negative infinity to infinity, or all real numbers is the domain here. You can do the 5th root of positive, negatives, or 0. So, in summary, if we're taking the nth root, 1 over n, if n is even, the domain is 0 to infinity. Can't get negative numbers taking it to an even power. But if it's odd, it can be all real numbers. You can get positive and negative, so you could write it this way or that way. All right. The only thing I wanted you to do here is if you type this into your calculator, you'll get a decimal. You type this in the calculator, you get the square root of 17 again. If you type this in the calculator, you get the square root of 17. These are all the same. So you could call them all the square root of 17, or 17 to the 1/2, or 17 to the 0.5. Or you could write the decimal approximation for all those, but they're all the same. Which is my setup to try to make you think that these are all the same, and they're not. They're most definitely not. So what can you take times itself 3 times and get -8? Well, if you take -2 times itself 3 times, you get -8. So the cube root of -8 is -2. This says the cube root of -8, -2. Now let's do it a different way. -8 is -2 times -2 times -2, or -2 to the 3rd. And then if we take it to the 1/3 power, if you got a base to a power to a power, you multiply. So 3 times 1/3 is 1. So you get -2 to the 1, which is -2. Now, I don't know how many times I've seen people call 1/3 0.3. 1/3 is 0.3333, repeating to infinity. This is just 0.3, which I hope you know is 3/10, which can be thought of as, well, -8 we know is -2 3 times to the 3 to the 1/10, or we can just call this, or I'll just do this, -8 to the 3 to the 1/10, or it can be thought of as -8 to the 1/10 to the 3, because 3 times 1/10, or 1/10 times 3, is 3/10. And you notice that no matter which way I think about it, of any of these, I'm taking the 10th root, an even root of a negative. I can't do even roots of negatives, only positive. So this one doesn't simplify in the real numbers. It's an imaginary number. It's an imaginary. Okay? And it's not just an I, it's messy. So now the next one, I put this one here just because people get on the calculator and of Desmos or a calculator or whatever, and they just start typing away and thinking, okay, -1 squared, but typing this, well, that means -1 times -1, which is 1. Great. In this one, they say, oh, that's -1 times -1, it's 1. But if you type this in the calculator just like this, you get -1. And it frustrates some students. But you have to understand the order of operations. A negative on a 1 or a 8 or a negative on anything is like -1 times it. So I can think of this as -1 times 1 squared. Now, if I got parentheses, I have to multiply these first and then square it. If I don't have parentheses, I have -1 times 1 squared. I have to do the squared first and then multiply by this. So 1 squared is 1 times the -1 is -1. I want you to understand the difference between this and this. Order of operations say square the whole thing. Order of operations says square the 1 and then make it times a negative. That's why that comes out to be negative. And this is positive. Now this one, we've got negative 1 to the 2/10. And at first glance, it looks like it's an even root, 10. But this fraction simplifies to 1/5. So it's an odd root, and this can be done. The 5th root of negative 1 is negative 1. You can type this one in the calculator. It'll say imaginary, non-real, or something. If you type this one in the calculator, it'll give you negative 1, if it's a smart calculator. Now, the point of this one is, does it matter whether the 2's inside or outside? If you think of this in terms of the exponents way of looking at things, you can see that these are the same. It's negative 27 to the 2 to the 1/3. You're supposed to multiply these, but you can multiply them in either order, so it could be negative 27 to the 1/3 to the 2. Says do the cube root first and then square it. This says square it and then do the cube root. They are the same because when you multiply these, we get negative 27 to the 2/3. The 3 means cube root. Well, 27, a negative 27 is negative 3 times negative 3 times negative 3. So it's negative 3 to the 3rd to the, that's the 27, negative 27, to the 2 to the 1/3. So 3 times 2 is 6, divided by 3 is back to 2, so this is just negative 3 squared, which is 9. Or if you wanted to do it the other way, negative 27 is negative 3 times negative 3 times negative 3. And you're going to do it twice. And then you're going to take out groups of 3. Well, there's one negative 3, and there's another negative 3, giving us negative 3 squared, which is 9. Now, if you do it the other way around, you got negative 3 times negative 3 times negative 3. And you take the cube root. So anything that's 3 times will come out as a single, so we get negative 3 out. But we're supposed to square that, because the square was inside first, so we did that, and then we take the cube root. This one says take the cube root of this, and then square it. Well, negative 3 times negative 3 is still 9. And this says take the cube root of 27 and square it, or takes the negative 27 and square it, and then take the cube root. It's both of these, either written this way or this way. This is the same thing, and it comes out to be 9. Number 3. We're looking for groups of 3. Well, 8 is 2 times 2 times 2. X, 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 Y, 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 Y. Groups of 3. That's a 2. That's an X. That's a Y. And we got 2 Y's that we couldn't pull out, so they stay in the cube root. Y times Y is Y squared. And this is my answer. It could also be written as 2xy times y to the 2/3. Cube root squared, or y squared cube root. You could write this part as the cube root of y squared, or you could write it this way with that in front. And this says the same thing, cube root of the same thing. So if you think of this 2 as 2 to the third, x to the third, y to the fifth, to the 1/3 power, then if you distribute the 1/3, if these are all multiplied in here, you can distribute the 1/3. So 1/3 times 3 is 2 to the 3/3. 3 times 1/3 is x to the 3/3. 5 times 1/3 is y to the 5/3. And 3/3 is 1, so this is just 2. X to the 1 is just x. Y to the 5/3, that's an improper fraction. This is the same as y to the 1 2/3. So y to the 1 is a y. This is the same as y to the 1 times y to the 2/3, because if you're multiplying, you add the powers and you get 1 2/3. So we get y to the 2/3, which can be written this way, or left this way. So this simplifies to this, or this, or this. This and this are the same. This one, when there's an addition, I'm going to take a little time and explain why you cannot distribute the 1/3 to these. A real common mistake for math students when they're learning mathematics, doing the Pythagorean theorem, and you get a squared plus b squared equals c squared, and then you take the square root. So you get something like the square root of 9 plus 16. And some students say, oh, okay, I'm just going to call that 3 plus 4, which is 7. And they check their answer. That squared should be whatever this is. 7 squared is 49. 9 plus 16 is only 25. This does not check. This 3 plus 4 is 7, but it's not the square root of this. 9 plus 16 is 25, and the square root of 25 is 5. This is the correct answer to this. 5 squared is 25, and 9 plus 16 is 25. Now, why doesn't this work? So I'm going to do x squared plus y squared as square root, or if you will, x squared plus y squared to the 1/2, and people want to distribute this and call this x plus y. Or the square root of x squared is x, and the square root of y squared is y. This is not true. This is fine to there, but that's not true. Now I can show you that it's not true by, if this is the square root, I should be able to take it times itself and get back to this. X times x, x times y. Oops, I don't have any xy's. And then y times x, that's another one of these xy's. And then y times y. If this was the square root of this times itself should make this. It doesn't. It has an extra piece in it. That's extra piece is huge. It means you cannot distribute a power over something, two parts that are subtracted. You cannot take the square root of this piece. This is like saying to the 1/2 power, and you can't distribute the half to each piece. That's why this does not work, that you have to add them together. So here the temptation is to distribute the cube root. Take the cube root of that, take the cube root of that, take the cube root of that. That plus messes it all up. You cannot distribute the third, so this is already simplified. Can't simplify anymore. Okay. Page 2. Half, square root, same. This should be pretty easy. See, 20, that's 2 times 10, which is 2 times 5. So if I'm doing it in powers, this is 2 squared, 5 to the 1, x to the 3rd, y to the 4th, all to the 1/2. These are all multiplied, so I can distribute the power, and I have to do it to everything. 2 times 1/2 is 1. 5 to the 1 times the half is 5 to the 1/2. X to the 3 times the 1/2, x to the 3/2, and y to the 4/2. 2 to the 1 is just 2. 5 to the 1/2 is still the square root of 5, so I'm just going to leave it 5 to the 1/2. X to the 3/2. 3/2 is 1 and 1/2, so I can write x to the 1 and x to the 1/2. If I were to multiply these, I get x to the 1 plus 1/2, or x to the 3/2. 4/2 reduces to 2, so it's y to the 2. Now, another way to look at this is 2xy squared, square root of 5 still, and the x still. And there's something wrong. This is an even root, and so if I were to square, even if x was a negative number, and I squared it, or cubed it, I get a negative, and if I take it, a pair of them out, the two negatives turn into a positive. So, but this was a negative number. I didn't explain that very well. I'm taking, let's look at it here. I have 2 times 2 times 5 times x, 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 y, 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 y. I'm taking out pairs. A pair of 2's is a 2. 5, can't take it out, so I still have square root of 5. A pair of x's come out as an x. If x was 2, 2 times 2 is 4, square root of 4 is 2, what x was. But if x is negative 2, negative 2 times negative 2 is positive 4, the square root is a positive 2, but I made x be negative. I need to change that. Any negative number that was in here needs to go to a positive, so I need to put absolute value of x. Even roots, I have to make sure what I take out as a variable is positive. Now, there's another x left. If I have 2 y's here, that comes out as a y. Another pair comes out as another y, so I get y squared. I could put absolute value on it because I'm doing even root, but a number, any number, squared is positive already, so the absolute value would be redundant, unnecessary. So here, when I call this x to the 1, but it needs to be positive, so I need to put absolute value on that. This one, we've got subtraction and addition in here. I can't distribute the power, so this is already simplified. Can't do any more. All right. Fourth root, even, so it's going to be some absolute value involved. Probably. Now, if you don't recognize 144 as 12 times 12 from your multiplication tables, you should recognize it as even, which means 2 times something makes it. And if you do some arithmetic, you get 72, which is even, so 2 goes into 72. And that's 36, which is even, so 2 goes into 36. is 2 times 18. 18 is even, so it's 2 times 9, which is 3 times 3. And we got y, oh, x. X, 5 times y, 8 times. Groups of 4. 4 twos is a 2. If it's an even root and comes out as a single, I need to put absolute value, but 2 is already positive, so I don't have to put it on there. I have 2 3s. They won't come out, so I still have 4th root of 3. I have 5 x's. 4 of them come out. If I take 4 of them and multiply it, even if it's negative, it turns to positive. I pull it out, it turns positive. So this has got to be absolute value. And there's 1 left. And y to the 8th, there's 2 groups of 4, so it's y squared. That's doing it this method. Let's do the same problem with the power method. 144 is 2 to the 4th, 3 squared, x to the 5, y to the 8th, to the 1/4 power. So 1/4 times 4 is 4/4. 1/4 times 2 is 2/4. 1/4 times 5 is 5/4. 1/4 times 8 is 8/4. 4/4 is 1. 2/4 would be 3 squared 4th root. 4th root of 3 squared. I should have a square on that. 3 times 3. There's 2 of them. I was thinking ahead. But 3 to the 2/4, 2/4 reduces to the 1/2. So I could write that as the square root of 3 if I wanted. Or 3 to the 1/2. X to the 5/4. 5/4 is 1 and 1/4. So I have a x and an x to the 1/4 left over, 1 and 1/4, and I have y to 8/4 is 2. This is an even root that I'm doing, so if anything it could possibly be negative, we need to change it to positive. And this is still in the root sign. Oh, and yeah. Now, the square root of 3, that's 3 to the 1/2, is the same as 3 to the 2/4, and 3 squared is 9 to the 1/4 or 4th root. So the 4th root of 9, which I have here, is also the square root of 3. 3 to the 1/2 is 3 to the 2/4. That's what I wanted you to see in that one, doing it this way. Now this one is the same as this, except it's cubed. So if I do it this way, I got to write it out 2, 2, 2, 2, 3, 3, x, 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 y, 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 2, 3, 4, 5, 6, 7, 8. Again, two, 3, 4, 5, 6, 7, 8. And again, 3 of them. 2, 2, 2, 2, x, 3, 3, x, 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 y, 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 y. That's the stuff inside to the 3rd. Taking out groups of 4. 1, 2, 2, 2, 3 2s. 2 to the 3rd. Or 8. 2 3s plus these 2 3s is 4 3s, which would come out as a 3, and there'd be 2 3s left under, which is 9. 4x's, 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 that leaves an extra x in each one of those, so that's x to the third that doesn't come out, and x comes out 1, 2, 3 times. 3 groups of 4 comes out as 3. That could be an odd power, a negative to an odd, could be negative, so we got to make it positive on an even root. And then a group of 4, 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 of 4 and 4. So that's 1, 2, 3, 4, 5, 6 groups of 4. And every group of 4 is a y, so it's y to the 6th. And y to the 6th is always positive, so I'm done. Now this one would have been easier to do in powers. 2 to the 4th, 3 squared, x to the 5, y to the 8th, to the 3, to the 1/4. Well, 3 times 1/4 is 3/4, so I got to take 3/4 times each of these, and these are all added, or multiplied, so I can distribute the power. So 3/4 times 4, 12/4, or 3. So I get 2 to the 3rd, which is the 8. 3 to the 2 to the 3/4. 2 times 3/4 is 6/4, which is 1 2/4. So I could write it as 3 squared 4th root for that part, and it's also x. No, I'm doing the 3's. 3 to the 6/4, which is 3 to the 1 2/4. So I got 4th and 2 of them. 3 squared, 9. But also 2/4 reduces to 1/2, so I could call it just the square root of 3. 4th root of 9 is the square root of 3. But anyway, either way. X's. 3 of them, or 4 of them, 4 of them, and 4 of them 3 times, so I get x to the 3rd. It's odd coming out of an even, so it needs to be positive if it comes out of an even, so I have to put absolute value on it. That leaves 1, 2, 3 x's in, but if I do it this way, 5 times 3/4, that's 15/4. 15/4 is 3 3/4. So I get x to the 3rd and the 4th root of x 3 times. And the y. 3/4 times 8 is 6. 3/4 times 8 is 24/4, which is 6. So this is pointing out the power one shows that the 4th root of 9 could be the square root of 3, 4th root of x to the 3rd. This could be simplified to that if you wanted. And finally, the last one, there's a plus. You can't distribute the 3 or the 4, 1/4, so this is simplified.